Okay. Good afternoon, everybody. Let's start with some descriptive statistics about the exam. Let's see if it is on. Yeah, this is on. This is only for on-campus students. For distance learning students, I already sent basically the descriptive statistics as in an announcement. So as you can see, mean is 64.5. We have a huge standard deviation. Mean is 12. Minimum is 12. Maximum is 97. We didn't have, unfortunately, any 100. So the third quartile, it's good. It's around 80. And median is 69. It's a little bit skewed. But most, as you can see, we have more than, let's say, 25% greater than 75, which is good. So how did I do curving? First, I start with calculating 95th percentile. Your class is 93.3. Then I found the difference between this number and 100, and I added, I cannot use mouse, I don't know why, 6.7 to each grade. Okay, and now your grades are updated on T-square. So what you have on T-square is different from what you have on your papers, but because of this curving. Any questions? Yeah.
How do you map your number grades to letter grades for your class?
It depends. So I do some. Yeah, actually, I do some statistical analysis. That's why I cannot say. I try to find the gaps, and then that would be the criterion for A, B, and C, where the gaps are. So that's how it works. So it's not crisp 90 because maybe none of you can get A at the end of the day. But no, that's not going to be like that. Again, I do some statistical analysis for finding the threshold for each letter grade. Any other questions? Yep.
Get the 95th percentile?
Yep, yep. So why did I do that?
Percentile.
That's what I do every time, just 95 percentile. Yeah. So because I want, if I do 50%, so 50% of you guys get A. I mean, like 100, if I pick 50 percentile or the median. So 95% means 5% of the grade's going to be at the end of the day 100. So more than that doesn't really make sense. Do you know what I mean? Yeah.
Not like something that...
Oh, no, statistical. Oh, yeah, that part, no. This is just some personal thing. Yeah, it's personal. I said 95%. Yeah, yep, go ahead.
Get a feel for our letter grade from the grade right now, even from the curves?
No, if you want, I need to do some analysis on that. Yeah. So, but if you are more than 90, you are in good shape, definitely. Yeah, question?
I'm just curious, with a standard deviation that big, is that not a consideration that you take?
No, actually, the standard deviation is because we have a couple of very low number. That standard deviation is basically very sensitive to those numbers. That's why you can see the difference between median and mean is like 5 units, which is huge. So, because mean is sensitive to sort of like very small numbers or very large numbers, but median is not. Yeah. Any other questions?
So say you perform poorly, should we come speak to you about...
Yeah, actually try to put it this way. If you do a better job in the second exam, then I consider it, okay? So what I do at the end of the day, I try to have a float, basically a float like weights, okay? So right now it's like 20, 25, 25, 25 or something like that. But if you do a better job in the second exam, I basically consider that and change the weight a little bit. Yeah, that's for everybody. Yeah. Any other questions? You good here? Okay. Now, so it's almost half of semester. I want to get some feedback from you guys. Yeah, after test grades, exactly. That's important because it's part of it. I give you a few minutes. Yeah, that's okay. So you don't need to write down your names. That's important. So write whatever you want to say. Yes.
Was there a kind of statistic of how well people did on certain sections?
No, I don't have this one. That's a good question. No, I don't have this analysis. Yes. Homework? No. Like, but I think you can see this on TS code. You cannot? No? You mean the mean and... no, I don't have it right now, but I can... Yeah, I can figure out what would be the average for homework if you want. Yeah. Okay, so quick review on basically inferences for mean of two population. When variance is known, we said, okay, in this case, we use Z distribution, and there are, again, three methods. Could be use critical region, we could use high confidence interval, or p-values. Then we said, what if the variances are unknown, and we had two basically cases, variances unknown, but they are equal. In this case, we use T distribution, and we estimate the common variance by pooled variance estimator, which is the weighted average of two sample variances for two populations. The second case is when the variances are unknown and unequal. They are not equal. Then we use an approximate T distribution with this number of degrees of freedom. And if the variances are equal, we use the second method. Our result is going to be very similar. We had one example. And another type was pair t-test, where you have a pair of observations and the observation from the first sample and second sample are not independent. For example, if you want to see the effectiveness of a diet program, you randomly select a number of people, you measure the weight before the diet program and after diet program. So you have two numbers for each person, and since you are using one person for each pair, those two numbers are dependent, and in this case, so it's like before and after, then what we need to do, we need to calculate di, which is basically the difference of these two observations, and instead of basically making inferences on original observations, we make inferences on basically the difference. So difference is just one population, and we want to see if the mu of d is equal to some number or not. Okay? And again, that's going to be a simple t-test with n-1 degrees of freedom, and n is the number of paired samples. Any question? Is it clear? Yeah.
This one, you assume that n1 is equal to n2, but for the other ones, when you're comparing two distributions, it's 2n-1, right? That's the difference between.
Oh, no. What I'm saying is, so let's say for this one, we need to have equal n because it's a pair of observations. Okay, for t-test, pair t. So this is pair t. So the number of observations for two populations should be the same. If not, you need to remove, for example, let's say one of them is 10, the other one is 8. You need to remove two of them to make them pair. Okay? For the other one, which is two-sample t-test, so one could be n1, the other one could be n2. Okay? So that's the first difference. The second difference is the degrees of freedom for this guy would be what? n-1. Degrees of freedom for this guy is n1 plus n2 minus 1. Okay? That's the second difference. So they don't have basically the same degrees of freedom. But now the question is, let's say you have a two-sample case where first sample and first population, let's say, and the second population are independent. Okay? They are not dependent like this. Somebody may ask why you are not calculating di for this guy and then use pair t. Okay? Although they are independent, we can use the same procedure. Does it make sense? So the answer is, let's say in this case, n1 and n2 are the same thing. Okay? So what is the degrees of freedom for this guy? It's 2n minus 1. This is 2. 2n minus 2. Okay? So the degrees of freedom here is 2 times n minus 1. Degrees of freedom for this case is n minus 1. So here you have more power compared to this case. So when you have two independent samples, the best way or the more powerful way of hypothesis testing is either this guy or this guy, because it has more degrees of freedom and more power. Okay? Here, by subtracting two pairs, you are losing some powers because you are losing some potential sample size. Does it make sense? Okay. Any other questions?
In the case of the two-sample, are we using an F distribution? Or a T?
You are talking about mean right now. Yeah. Just T distribution. So now, back to your point, what if we want to compare variances of two populations? Okay? So if we have two populations, we want to do some hypothesis testing on the variance of these two populations, and we use F-test. Our test statistics is the ratio of the sample variance. Okay? This is null hypothesis, and these are different alternatives that we have. These are rejection regions. And we can also use basically the confidence interval method. Find the lower confidence interval and upper confidence interval. What should we compare? 1. Why? Because under H null, sigma 1 over sigma 2 is going to be 1. If this confidence interval includes number 1, then we cannot reject, otherwise we reject it. Does it make sense? So the confidence interval, we compared it with 1. Why? Because sigma 1 squared divided by sigma 2 squared under H null is what? Is 1. Okay? Because it says they are equal. Any questions? Is it clear? Okay, one example. We have, in a process, oxide layers on semiconductor wafers are etched in a mixture of gases to achieve the proper thickness. The variability in the thickness of these oxide layers is a critical characteristic. So we are interested in low variability. We have 2 different mixture of gases, and we perform some experiment. 20 wafers are etched in each gas, and we calculated the sample standard deviation of oxide thickness. For the first batch of 20, S1 is 1.96. For the second batch is 2.13. So is there any evidence to indicate either gas is preferable? So I know we are talking about variability. This is my H null. How about alternative? Greater than, less than, unequal. Why? Because it says either gas. Okay? When it says either gas, could be this greater than this, or the other one greater than. Sigma squared greater than sigma squared 1. So it's inequality. Okay? So what should we do? We calculate F0, which is S1 squared divided by S2 squared. In this case is 1.96 squared divided by 2.13 squared. And that number is 0.085. And we compare it with, if I go back, so we have 2 critical regions to compare with, this one and this one. So if alpha is 0.05, so our N1 and N2 are the same thing, is 20, and alpha is 0.05, so we need to find F of 0.025. And 1 minus 1, which is 20 minus 1 and 20 minus 1. This is 2.53. And we also need to find this guy, 1 minus alpha over 2, with the same degrees of freedom. Okay? And then we compare it with F0. This guy is 0.04. So 0.85 is between 0.40 and 253. Therefore, there is no evidence for rejecting H naught. We do not reject it. Because the critical region is F0 is greater than either of these 2 numbers. Does it make sense? Any questions?
Where 1 falls in that distribution, or just that our F0 falls between?
You mean in terms of what?
For deciding whether or not we reject H null.
No, if you just compare it with these two thresholds. If it is greater than the upper threshold, you reject it. If it is less than the lower threshold, you reject it. So it's not absolute value because f is not symmetric around 0. That's the only thing.
What does the statement in the parentheses right there have to do
Oh,
with?
that one is for confidence interval. So we have two methods. So I'm using this method, the first method. Okay?
Oh, okay.
Yeah,
Okay.
that one is for confidence interval. If you find
Okay.
the confidence interval, then you compare it with 1. So if that confidence interval includes 1, you cannot reject. If it doesn't include 1, you reject it. That's another method, yeah. You can solve it, basically this problem with the confidence interval as well. Okay? Does that make sense? Any questions? No questions? Okay, quiz time. Okay, so group of 3. I think group of 3 should be fine. Yeah. Just one from top and one from bottom, and pass it to the next one. Oops. Yeah, thank you. So group of 3, 1 would be basically coordinator, and 2 gonna be two of you gonna be appraisers or like operators. So what you are gonna do, you are gonna make some measurements, and then answer the hypothesis testing. Yes, answer the hypothesis testing on the sheet. So whether the performance of 2 appraisers are gonna be the same or not. So and assume alpha is 0.05. I don't think I put it there, but anyways, so you have, can I borrow your sheets? Yeah. So what happens, you have 8 parts to measure. What you are going to do, you are going to measure the length of the parts, okay, for each part. And so part 1 to part A, appraiser 1 and appraiser 2, okay? So that's how it works. And then after you have the data, then you need to decide basically what type of hypothesis testing you need to use and answer this question, whether 2 appraisers or 2 operators are performing equally in terms of measurements. Okay? So the question is not about the length of the part. It's about whether they have the same performance in measurement or not. Okay? Okay, and you can... So, yeah, this is basically, so you can just